All right, this lesson is going to be relating to this one problem here, this one skill, which is to look at a rotational system, in this case, which is some sort of beam. And just to put that in perspective, um, this could be thought of as a beam. And, it can rotate. If I were to put my finger here, of course, that's considered a rotation. Staying put here on my finger, but this part is now falling. And since that's not falling straight down, it's actually, this part is staying still. It's actually considered a rotation, right? If I were to let go of it. And again, the axis that it can rotate out on depends on where the pivot point is. If this is my fingers as the pivot point here, then that's the axis of rotation, and the whole beam will rotate about that axis. If I were to slide my fingers here and let go, now it's rotating about an axis that goes straight through my fingers where it's being held. And that axis is actually goes straight through my fingers where I was holding it. And now it's pointing right at the camera. And so this one that's pointing at the camera, this one is considered the axis of rotation. It's an imaginary axis that we imagine because the point of rotation is along that axis and that axis. And then it can rotate about that axis, around that axis. When we say about the axis, we mean around that axis. And how it rotates, in terms of how rapidly it rotates, depends on how much torque is being generated as it is applied around the beam or around the rod. And so for that reason, we have to certainly develop a strong ability to understand how to add up multiple torques to get what's called the net torque. In a similar way, in linear kinematics, in order to determine how quickly something speeds up in a linear sense, if it's a box that you're pushing, to determine that acceleration rate, we would need to know what the net force was. Now we're talking about net torque. And if I was pushing it across a flat surface that has friction, then I'd have to know, well, the net force is the unbalanced amount. That's the amount that creates the acceleration. And I'd have to do my applied force minus any frictional force back to get the unbalanced amount. And then we can use it, Newton's second law, A equals F net over M, plug in the mass of the box, the net unbalanced force, solve for the acceleration. We're, again, going through similar steps in this unit, and that's where we're headed next. First, you learn about torque. It's like learning about forces. Then you learn about net torque, which is like learning about net forces when there's more than one force on a box if it's moving sideways. And then we pull in Newton's second law, which will be that the angular acceleration alpha, how rapidly this stick rotates through its angle. It's really not correctly said. That's more like omega. The angular acceleration is how rapidly the rotational speed, omega, increases per second as it rotates. If it starts out falling with a slow rotational speed, but then gains rotational speed and then gains rotational speed, then we know it's accelerating because each interval of time it's going through a greater angle. And ultimately in physics, we might want to know, what is that rotational angular acceleration rate, symbol alpha? Same thing as like saying, what's the linear acceleration A? Well, you need to know what the net force is, and you need to know what the mass is. Same thing for this rod. We're going to need to be able to work out what the net torque is. And then next week, we're going to talk about the mass, how the mass, known as the rotational inertia of this, which is how much it resists being rotated, just like mass is a measure of how much something that you're pushing resists being accelerated. Heavier objects will gain rotational speed more slowly. And that lesson comes next week, rotational inertia. It's the similarity or analogy to M, mass. And they all come together in Newton's second law for rotation. And that comes maybe toward the end of next week. So that's giving you the global view of what we're doing and where this is headed. But you have to be able to do this sort of problem. This problem, again, shows a beam like this that can either rotate with the central dot being the axis of rotation, which is like this, and that's called point C, or we can imagine shifting my fingers, which are currently at point C, the middle of this rod, a little bit over to the left, like this, and calling that point O, and now recognizing that that can also rotate, like we're seeing around point O, or about the axis that goes through point O. And to figure out, again, which way it rotates, if it, in my case, when I'm doing this just with my stick, it's just gravity. Gravity is the downward force that creates the torque on the stick. But in this case, we're not referencing gravity. We're referencing 3 different forces. They could be, ropes that are pulling at those angles. And each of those ropes is creating a torque. And some of them are reinforcing each other, meaning that some of those forces are on the same team trying to get this thing to spin in the same direction, while there might be a couple that are on opposite teams. One of those forces might be getting torque that causes it to rotate this way, while the other might get a torque that causes it to rotate the other way. Those are on opposite teams. They're not reinforcing each other. They're subtracting from each other. So they'd have to be opposite signs, 1 plus, 1 minus. And ultimately, we have to be able to work out what those individual torques are and add them up, some with pluses, some with minuses, to figure out what the net torque is. And that's the purpose of this lesson. So let's start it. Move this over to the side. Maybe a little smaller. I think of the best way to view this. Let me see. Like this, I think. There we go. Yeah. And now I can pull up that. Okay. So let's begin. Where is my smart pen? Here it is. So here is our am I kidding? Why am I getting a line that's doing something funky right now? Kidding, right? Why am I getting these lines just appearing on the screen? Don't do this to me now. Oh my good Lord. All right. I guess I'm going to have to see if I can pause this video, figure out what's going on. I thought it was working fine. Just they came in and fixed it the other day. I don't know. Let's see, am I able to pause a recording? I don't even think I can, unfortunately. No, give me 1 second, see if I can fix this. Now, let me just reset this program. I did try it out yesterday after they said it was fixed, and it was working fine. No lines were popping across my screen. It was just happening. Let's try again. Okay, seems to be working there. Maybe something weird was happening. I don't know. All right, so let's try again. Let me pull up the image again. I wonder if it has to do with the fact that it was not full screened. It's possible. So let me actually just jot it down then. To prevent any more waste of time here. 30 newtons, 45 degrees. I'm just going to put this onto a piece of paper and then copy it onto the board. 25 newtons. That one was 30 degrees. And then we had 10 newtons. That was 20 degrees. And then we were given distances of 2 meters and 2 meters on the other side. All right, that's all I really need to know. And this was one of the points. This was the other point. Okay. So I'm going to go ahead and close that, or just minimize it. Now maximize this one. So what we have is a beam with a force applied. Let me make the center spot. And now we have a force being applied here. It looked like at an angle of 40. Was it 40 degrees or was it 45? Can't tell what I wrote down. Sorry. It's 45. I'm going to check because it looked like I wrote 40. So this was 45 degrees. And it was 30 newtons of force, applied force, at a distance from the axis of rotation. You always want to work out what that distance is, straight from where the force is applied, which is here, straight back to the axis of rotation. And that's considered R, and that was a 2 meter distance. And then we had another force being applied right at the center of mass of this beam, which was 25 newtons. This was given a 30-degree angle. And then we were giving another force over here that was now going down at an angle of 20 degrees. And that amount of force was 10 newtons. So the ultimate question is, what is the net torque, assuming that this distance here is also a 2-meter distance? So what we need, well, let's start with part A. Part A says determine the net torque about, they have to just tell you which axis point, where the point of the axis is. So for the first part, they asked it to be for point, I think they called this O, which would be an axis that goes straight through the board like this. And we imagine that this thing can now rotate like this around that axis that goes straight into the paper, straight into the board, straight into the desk if you're staring down at a desk. So we're going to start with that. This is going to be our first axis of rotation. Let's just put AR for axis of rotation. So again, what we're focusing on are the perpendicular components perpendicular to R. Okay. So for that first point that I'm referencing, which is right here, if it's rotating around this point, if that is the point that it can rotate around, and the force is actually applied at that position, then what would R be? Right? Because if it's, again, if it can rotate around this point, if we looked at the other force, let's call this one F1. So I can reference them. This one will be F2. Let's call this one F3. If we look at F2, at least it's being applied at a distance of 2 meters from this axis of rotation. So it's going to get some torque, because remember that torque is how far it is from the axis of rotation in terms of where the force is being applied, how much force we're talking about, and sine theta. And remembering that FA sine theta is the perpendicular force perpendicular to R. The amount of force perpendicular to R. Because R is actually a vector. It goes from the axis of rotation straight out to where the force is being applied. So in fact, let me actually draw that in a little better. And this has to move because this is now in the way. So let me point out that this here, what I have here is R, is really a vector, right? So R goes out like this. It's a vector. So what you want to do again is imagine extending R as a reference point, like I had said during class, and so that you can see the angle between R and F, which in this case, the angle between R, which is here, and F is that 45-degree angle. However, how far away is it from the axis of rotation? How far away is the force being applied, which is right here, from the axis? It's on the axis of rotation. There is no R. In an analogy, it's like going over to a door, opening it a little bit so it's not physically closed with the latch, just so it's loose, and then trying to put your finger into the door and push only a few millimeters away from where the hinges are, right? For a door that's opening, your handle's over here. This is the axis of rotation right here. This is the axis of rotation. This is R. And then you apply a force normally with the handle there, and you're getting some torque equal to R times F. But if you come over to this spot and try to apply a force there, what would R be? How far away is your finger from the axis of rotation? Well, it's none. So the door won't move. You can try it. Open up a door and try it. It won't move. You're not getting any torque. You're apply as much force as you want. As there's no distance from the axis of rotation, you can't get torque. The door won't rotate, because technically an opening door is a rotating door. It goes around a circle. So my point being is that F1 gets no torque because R is 0. For F1, it's being applied at the axis of rotation. It's a very important thing you need to know for these types of problems. If the force is applied at the axis of rotation, you can ignore it. It's getting no torque. Again, I just plug in 0 for R, and torque 1 would be 0. Let me point out that what we're doing is net torque, and it's going to be equal to torque 1 plus torque 2 plus torque 3, because we have 3 forces that all can potentially get different torques. I'm not suggesting they're all going to be plus. We're adding them up. Some might have to be minus, some might have to be plus, and we'll deal with that in a minute. But once we assign certain signs to them, then we add up the results to get the net torque. That's what we're doing. So torque 1 is 0. Now we move over to force number 2, which is over here. We would now want to think, well, we have to be able to visualize that perpendicular component, which is right here, F perpendicular. And to work out, and remember there's a parallel part 2, F parallel, but F parallel won't get any torque because R, if I was to now draw R for that force, R actually goes from the axis of rotation straight out to where F2 is being applied. So it starts here and goes out to here. This is now R2. And so we're trying to find which component of F2 is perpendicular to this R. Well, it's this one right here, F perpendicular. That's the one that gets torque. The other one would just stretch out the rod. It wouldn't cause rotation. So F perpendicular, remember, is this is opposite. And this is where you'd have to be careful. This is where I warn you, because notice that they've given me an angle up measured to the vertical line of 30 degrees. Yet I've drawn a triangle that's on the opposite side of their triangle. So you have to be careful. This is a point of caution. For me, which I'm about to do, I'm about to write magnitude of the applied force at this spot times the sine of angle, sine of theta, because I'm looking at this angle, this theta. Well, that's not 30 degrees, that's 60 degrees, right? Because 30 plus 60 has to be 90. So this is where you have to be careful. You're looking at those angles, really think about it and look at it to make sure it all makes sense. So for me to represent that amount of perpendicular force, I would reference rather the total pulling force that's in this direction, which was 25 newtons, times the sine of 60. If I want to work out how much torque that particular component, F perpendicular, is getting, I'd write it as torque 2 equals the perpendicular force from torque 2 times whatever R2 is. Now I know 25 sine 60 is that perpendicular amount of force because I have it right above. I just did that. Times whatever R2 is. In the picture, they had shown R as 2 meters to the left and to the right of that central point. So that means this must be 2 meters. So I now know that this is 50, because 25 times 2 is 50 sine 60. My recommendation, again, is for any geometry-heavy units, and this one is, that you know your 45, 90s, because you're going to have to represent these as ratios, sine of 45. This is 1 root 2. This means if this is 1 foot from here to here, then if it was truly a 45, 90 triangle that you drew on a piece of paper, big piece of paper, I guess, and then this one would also measure 1 foot from here to here, and this one would be root 2 feet. Well, that's about 1.41 feet. From there to there, that's just guaranteed. Those would be the lengths because that's the ratios for a 1 root 2. 45, 90 triangle. So if I wanted to now reference not 45 but 60, then I have to know my other special triangle. I'm telling you have to have these. I have never bothered memorizing all of these because it's a waste of my time. Not to mention it would be hard. Don't do things that are hard if they're not necessary. Know the skills to be able to figure these out. The numbers, again, that go with the 45, 90 triangle are 1, 1, root 2. The root 2 has to go with the hypotenuse because it's the longest line. And root 2, which is 1.4, is bigger than the number 1, right? The 3 numbers you have to know over here are 1, 2, and root 3. 1 is the smallest number, which should go with the smallest segment. 1 would be this one. 2 is the biggest number, which needs to go with the longest line, which is this one. And root 3, it must be the third, just from process of elimination. So if I wanted to go over to my answer on the right side, which is 50 sine 60, and remove sine 60 and put some ratio in there, I'd think to myself, sine of anything is opposite over hypotenuse. coming to my special 30, 60, 90 triangle with these segments of 1, 2, root 3, I'd find my 60 degree. If I'm doing opposite over hypotenuse, because that's what sine of theta is, opposite would be root 3 over hypotenuse, which is 2. So this must be 50 times root 3 over 2. You're going to need to know how to do that. Because again, a lot of their multiple choice questions that do involve this kind of trig don't necessarily have sine 60, cos 45, or cos 30. They have these ratios. And if you don't have this skill, you might even know that it's 50 sine 60, but look down at their choices and say, I don't see 50 sine 60. What do? I see all these 50 root 3 over 2. You wouldn't be able to identify it, right? This is critical. So for me, to finish this F3 off, and I didn't mean to write F3. That's a mistake, just noticing that. That's torque 3. That's the torque that force 3. Force 3 was 25 newtons in magnitude. So the torque we're getting, this one is getting, which I should write as torque 3, is 50 sine 60, but sine 60 is root 3 over 2. Technically, 50 divided by 2 is 25. So I know this is 25 root 3, and the units would be newtons times meters. Those are the units for torque 3. I'm going to go ahead and call a rotation that is in this direction as a positive torque. Any torque that makes it rotate clockwise, I'm going to call positive torque. And any torque that makes it rotate counterclockwise, I'm going to call that a negative torque. Technically, it doesn't really matter which way you choose it. There are some more advanced parts of physics where it matters what the signs are, but if you're just trying to figure out which way does this thing overall rotate, clockwise or counterclockwise, which is often one of the questions, it's not just what is the net torque, it's what's the net torque and which way will it rotate. Doesn't matter whether you called this one minus and that one plus or switch them, just pick one and stick with it, and then just evaluate your result to make a conclusion. So torque 3, and I wrote the wrong thing there, didn't I? Torque 3. It's not torque 3, that's force 2. Force 2, another mistake, sorry. This one that I've been working on is force 2. So this is torque 2. So sorry. So since torque 2 alone, you have to think about what it's alone doing. Ignore all the others in terms of this part, in terms of what am I going to assign, a plus or a minus to my answer of 25 root 3. Well, torque 2, remember, has a component that's pointing up. So that upward pull, I think of this physically with my rod now in here. If I was to apply an upward force at that point, up, to represent F perpendicular, my rod would rotate up, right? Up is technically like this. That's actually counterclockwise, right? That's a counterclockwise rotation. Based on what I chose, I'm going to call it a negative torque based on what I had chosen right here. So I'm going to put a negative sign in there. I'm going to assign that. Now I have to just pay attention to this last one. I'm going to erase a lot of this because it's gotten so cluttered. So I will erase, I won't erase the bottom, but I'll erase that part. Now we have to take a look at this last force that's being applied, which has the 20-degree angle. And just do the same thing. We have to do the exact same process. So now we would say, okay, now we're looking over here at this one here. 10 newtons of force is applied at this angle of 20 degrees. Imagine my components. Doesn't seem like good location for that, so I'm going to erase that. So my components would go this way and down. Now I'll add that 20 degrees back in. So where is R? R is technically going from the axis of rotation, which I had to think about that for a minute because I forgot. It's all the way back on the left. This problem that I've started with is through point C. And point C was all the way back here. This is where I could rotate around. So R for this last force, which is applied where I'm coloring the circle in now, R would go all the way from here to all the way to there. So if it was 2 meters on the left side plus 2 meters on the right side, that would be a full distance of 4 meters away. meaning this last force that we're evaluating is being applied at a distance of 4 meters from the axis of rotation. So I'm going to go ahead and add that in. Here's the distance r. I can call it r, whatever this was. Is this r? What is this, 2 or 3? Remember, 3? This is r3. This is, I guess, force 3 that we're looking at now. So r3 is 4 meters. And remember, it's just the magnitude that matters. If that r vector was pointing to the left, and you wouldn't say -4 meters, you just say 4 meters. It's just the full distance. It's called the lever arm, the distance from the axis of rotation that you're applying your force, which creates leverage. That distance is called the lever arm. Anyways, it's just a positive number. So now let's just continue. So now we know that this one right here is perpendicular to r, which goes this way. So that's the one I'll call F perpendicular. Think to myself, okay, it's opposite to the 20-degree angle they've given me. Sine goes with opposite, so it's going to have to be F sine theta. What is that F? They gave it to me as 10 newtons. Sine. Now, in this case, I wouldn't be able to represent 20 as some sort of exact value, unless I tried to do some geometry thing, which is the sum of the differences that you can do to approximate these things, which no one expects you to do. If it's a 30, a 45, or a 60, then yeah, you might have to represent it as √3/2 or 1/2 or whatever it might be. But 20 degrees is not one of those special angles. So the most I can do is just leave it as it is, 10 sine 20. So how much torque is this one getting? The torque that this one is getting here would be that amount of force. Again, who is this one? This one was 1. This one was, I don't remember, 2. So this is 3. It would be the F perpendicular amount for force 3 times the distance, R3. Right? So the F perpendicular amount I have right there, right above it, 10 sine 20 times 4, right? Because that distance was 4. So I'd have torque 3 is 10 sine 20. This is F perpendicular for that particular force, F perpendicular times 4. This is R4. So now to simplify it, 10 times 4 on the other end is 40. So I know this should come out as 40 sine 20. So I'm going to write that underneath just because it's kind of messy. Torque 3 equals 40 sine and 20. Now I have to think, which way would it make this thing rotate by itself? Ignore all the others. Force 3 is all the way over here on the right. Imagine my stick like I'm doing on the board right now. And I notice that perpendicular component is actually pointing down. That's like me pushing down with my finger. That would actually cause a rotation that's a clockwise rotation. And based on this convention that I've created in the center of the board, a clockwise rotation, I'm going to represent as a positive torque. So that one can stay positive. Remembering that torque 1 is 0 because it was applied at the axis of rotation. Now, if we want to do the net torque, we just add them up. Okay, so now we say net torque is equal to the torque 1 plus torque 2 plus torque 3. And I'm also pointing out, it makes sense that torque 2 and torque 3 are different signs. One has to be plus, and one has to be minus, because one of them was trying to make this thing rotate clockwise, and the other one was trying to make it rotate counterclockwise. If you put them both as plus, that means they're reinforcing each other on the same team, trying to get this thing to rotate in the same direction, and those torques would add together. When things are on opposite teams fighting against each other, they have to be opposite signs, right? This one would have been 0 because the R was 0. This one would be now minus 25 √3. I don't know what that is as a number, but I don't really care right now. And then plus torque 3, which would have been 40 sine 20. So now I would break out a calculator and do it out. So I end up with 25 √3. 25 √3 was 43.3, according to my calculator. So this is negative 43.3 Newton meters of torque. And the other one created how much torque? Well, 40 sine 20 comes out as 13.68 Newton meters of torque. So which force is getting more torque? Torque 2 is. Torque 2 is getting almost 3 times, right? 14, 28, 42. That's just about a factor of 3. So torque 2 is getting almost 3 times as much torque. Let's try to make sense of why is that? Torque 2 is the one that's in the middle of my board here, one with the tall triangle. Torque 3 is the one that's over here on the right, the kind of thin triangle. Looking at the component right here, this component, number one, the magnitude of that force was 25, far greater than the magnitude of the force on the other side, which is only 10 newtons. And then the angle of 60 degrees geometrically allows for the perpendicular component to be a large percentage of that 25 newtons, right? While on the right side, the furthest side, 20 degrees is a pretty low angle. That causes there to actually be more parallel force than perpendicular force. It's not optimizing the torque, right? To optimize the torque, you want to actually be pulling at 90 degrees, which is straight down. And so as you swing that force that's being applied from the straight down direction, which would maximize the torque, that applied force now going this way causes that perpendicular component to get smaller and smaller and smaller and smaller, right? If this triangle right here was only a 5-degree angle, F perpendicular would be a tiny, tiny, visually a tiny little segment indicating that's a small amount of force, not going to get a lot of torque. Yeah, it was applied further away at 4 meters. That's in its advantage for getting torque. But the force that was being applied at that little extra distance was not enough to compensate. And so therefore it gets much less torque. All right, so that's more or less it. We would just add those together. 13.68 minus 43.3. I get the net torque. That's not correct. Minus 43. I get negative 29.62. Negative 29.62. That's what I'm getting, Newton meters, as my answer for the net torque. And then, I mean, if they said magnitude, then you just say 29.62 Newton meters. If they said in which direction will it rotate, if it came out as negative, which it did, the net torque came out as negative 29 point such and such. We have to come back to our picture to interpret, right? Negative I had decided to be as this way, which is actually counterclockwise, which means this thing should rotate counterclockwise, right? So the rotation, it'll be a counterclockwise rotation, the opposite direction of the direction hands on a clock rotate. Why? Because that middle one, the one in the middle, got more torque, right? And he was a lifting force, an upward force that overpowered the downward force on the right side. So the overall rotation would be up and around, up and to the left, and then around and down. I'm not going to spend the time to do the other one, but I'm just pointing out, if you were moving on to part B, which they did, now do the same exact thing for this point right in the middle, assuming that now your beam can rotate around that middle point. It would have been starting over again, but which force would have applied zero torque? Or which force would have created zero torque, I should say? Then the middle one, force 2. If the middle, again, is the axis of rotation, and force 2 is actually applied in the middle, it's just like pushing the door at the hinge. There's no leverage lever arm distance. And so you'd get no torque. So right away, you'd recognize that and say, oh, that one's 0. And then you'd turn your attention to the 2 endpoints, right? In fact, if you were doing that problem, you wouldn't have to do all of this over. You already have the geometrical part. F perpendiculars are already known for both of those. The only thing that would change would be R, because the axis of rotation is now shifted to the middle. And therefore, R would only be 2 meters for both of those forces on each side. And all I would do is come over here and take away the number 4 and put 2. And then in torque 1, I would come over wherever I had written torque. Well, actually, I would have to do torque 1, because originally I skipped it because it was 0 torque originally. But that's the idea. You would just repeat the exact same thing. Add them all up, interpret your sign to determine which direction it rotates, and then the magnitude of that number, like in this case, the magnitude of the net torque is 29.62 meters, Newton meters. It's just the overall quantity of torque. Later, that becomes important when they might say, at what rate does this thing gain rotational speed? Alpha. And we would have to use that number, the net torque. And we'll have to use this concept that this thing has some rotational inertia, which is some resistance to being rotated. Heavier things will rotate more slowly than lighter things. And so when we use this Newton's second law, which I teach you next week, for this problem, we would be incorporating our answer of the net torque being around what it is, negative 29.62, into the Newton's second law, which again is like A equals F net over M, similar to that. The F net is now net torque. And then the M is now this other symbol, which is capital I, which stands for the rotational inertia of this. It's how much it resists being rotated, like M. And then if you did what net torque divided by the rotational inertia, the number that pops out is alpha. And if you know alpha and the initial conditions, like did it start out with no rotational speed, omega initial is 0, then you should be able to predict all properties of this rotating system at any given time in the future after these forces are applied. Brings us back to rotational kinematics. You could predict that 12 seconds later, this thing should have such and such rotational speed, omega, by using kinematic formulas, because now you have alpha, right? That's the idea. And technically, then you could work out how much rotational energy it has or rotational momentum, which I know we haven't done that yet, but that stuff comes afterwards. Once you know what omega is, then you'll immediately know how much rotational momentum and rotational energy something has. Actually, you'd have to know omega and rotational inertia, but that comes later. All right, the lesson's over. I hope that helped. See you next time.